Excellent. Thanks, Janet. Yeah, thank you, everybody. Good afternoon. As Janet mentioned, my name is Marc Meyer. I'm at least temporarily the acting regional ecologist in Region 5, the Pacific Southwest region of the Forest Service, normally the Southern Sierra Province ecologist. And today I've been asked to talk to you about these climate trend summaries that we produce for the National Forest in California. I'm specifically talking about some of the trends in the Sierra Nevada bioregion when possible, those patterns and trends we're beginning to see in the on the Inyo National Forest in the Eastern Sierra. So a little bit of background about these documents. I was involved a number of years ago in the first iteration of these. These were produced by the Region 5 Ecology Program of the Forest Service. We produced these versions back in 2010, 2012, and initially supported some of the forest planning efforts, plan revision efforts, particularly in my experience, it was with the Giant Sequoia National Monument Plan that was being worked on at that time and some other planning efforts in the region. And since then, we saw that there was a high value of producing these types of documents across the region. So we created, as a program, we created them for all the national forests in Region 5, and that is in California for the most part. And we also summarized this information. If you wanted to see some of that summary in a public format, it is in the PSW General Technical Report 237. This is the Managing Sierra Nevada Forest shown in that little graphic there below. This is a publication that was edited and led by Malcolm North at PSW. And that chapter 3 really summarized some of these climate trends and information that we produced in that first iteration. And I'm pleased to announce that many of the newest versions have just been released in just the last several months. There's also a little bit of background of other related documents. If you wanted to dig into those climate trend summaries, I'll have a link for that later on in the presentation. But we have a lot of this information in terms of not just projected future trends in not so much climate, but climate-related impacts to ecosystems, summarized in these general technical reports focused on the natural range of variation. This also gets very much into that historical condition versus current condition in many of our forest and other ecosystems. And here's a couple examples for yellow pine mixed conifer. That was led by the former regional ecologist Hugh Safford, and the one for red fir subalpine that Malcolm and I worked on and published just 2-3 years ago. But the real purpose of these general technical reports is to summarize both the current and the future projected patterns in climate and their effects to natural resources, particularly terrestrial ecosystems and the such, and other resources. And there's a long list of authors, primarily in that Region 5 Ecology Program, and particularly want to acknowledge for those ones created for the Inyo, Sierra, and Sequoia National Forest, Marina Winchell, who was the, until recently, she was the Associate Province Ecologist here in the Southern Sierra. So she and a variety of the other ecologists led that work that I'm going to summarize to you today for, say, the Inyo National Forest Climate Trend Summary. There's a variety of applications. We've used these for forest plan revision, training Forest Service and other agency staff, informing Project NEPA, particularly when we develop restoration projects. The U.S. Forest Service climate change scorecards, this has been very handy. In some cases, it's also informed climate change vulnerability assessments to assess the vulnerability of different ecosystems and resources to climate change across the region. And it's also been really handy, and we've seen a number of external partners very interested in this type of information. So it's really designed to address a variety of these different areas and different information needs. The main topics we cover in here include climate, hydrology, fire regimes, vegetation, and wildlife. And for each of these, we try to provide some historical, historical just within, say, the 20th century and the beginning here of the 21st century. So might just be the last 20, 30, 40 years, or we dig back as far as we can in terms of that historical data or contemporary data. And then we try to provide some information about the projected future trends based on a summary of published scientific information on both the historical and future trends for each of these topics. And then it's worth emphasizing that we look at these, try to look at these at the forest level, but in many cases, we're focused more largely on these bioregional trends. So what trends that occur or patterns that occur within the Sierra Nevada bioregion here for these climate trend summaries, and specifically the one, the Inyo. And you can see here I'd say for the most part, our local patterns, we summarize based on local climate station data. But for many of these other topics, we just don't have a lot of that fine information that's located on the Inyo National Forest based on published studies or available data, because many of these other patterns, we've really just focused on the larger bioregional trends. So keep that in mind when I'm summarizing a lot of these trends in my subsequent slides. So let's dive into some of these patterns and trends that we're seeing. So in terms of recent climate, this is not going to be surprising to many of you. We've been seeing a pretty significant increase in temperature, about 3.5 to 5.8 degrees Fahrenheit since the 1890s. We've seen this based on a number of climate station data across the region, but particularly we're focusing also on some of this climate station data that's locally as well. And some of these other kind of related patterns to increasing temperatures include a frost-free period lengthening from 2 to 3 months. The greatest increase in these temperatures are often seen at nighttime. We often focus on those maximum temperatures, but the minimum temperatures is where we tend to see some of the greatest differences or greatest changes in temperature over time. And those have a lot of important implications. And then at the local scale, you know, a lot of these patterns we've seen bioregionally or statewide, but even at the local scale, we see this pattern is pretty clear and pretty strong. Droughts are definitely becoming more common at the bioregional scale or at larger scales within the Western US and California. But one thing to really emphasize is when it comes to precipitation, we often think of things as becoming drier. Well, in terms of the actual precipitation, we don't see a real consistent pattern in terms of the average precipitation, how that's changing. Things may be getting drier simply because as temperatures rise, you get greater rates of evapotranspiration, greater rates of moisture stress on vegetation as they transpire at higher rates. But in terms of actual precipitation, we don't see anything except perhaps a greater or an increased amount of variation in interannual precipitation over time. And this has become particularly evident since about the 1970s or 80s. We're beginning to see more of these extreme drought events, for example. In terms of recent hydrological trends, and I'll emphasize these are trends that are at the Sierra Nevada bioregional scale, so not at the specific forest scale, and particularly for elevations below 6,500 feet. We're seeing that peak runoff and stream flow have shifted to earlier in the year due to earlier snowmelt timing. And then snowmelt now occurs about 10 to 15 days on average earlier than compared to the early 1900s. And this is once again a bioregional pattern, and many of these studies are really focused on the west slope or west side of the Sierra Nevada. We're also seeing decreased groundwater storage evident during the 2012 to 2016 drought that we had in California, with more storage lost by evapotranspiration than is being recharged through precipitation. So during these drought events, we're seeing a real significant drawdown on that groundwater storage, in addition to our impacts and increased moisture stress on our ecosystems. Now, in terms of future climate and snowpack trends, what the temperatures are projected to increase by the end of the century. So we're talking about a little ways away from now, but this is when a lot of our greenhouse gas, increase in greenhouse gases is really ramping up the temperature increase across the globe, but also locally here. We're going to expect about a winter temperature increase of about 2 to 4 degrees Fahrenheit, summer temperature increase about 4 to 8 degrees Fahrenheit increase. And this is projected trends across the entire bioregion of the Sierra Nevada. Precipitation, though, remains highly uncertain and more variable, both in terms of amplitude, frequency, and the duration of extreme events. Some models projected that we might see more extreme events, as I said, spoke to in my earlier slide, based on past or recent trends. But there's a lot of uncertainty in those models and in the outputs of those models. So we don't really know for sure, but there is some of those projected increases that are expected in the 21st century. And then mid-elevation snowpack, that is about 4,000 to 8,000 feet elevation, is expected or predicted to decline about 30 to 65% by the end of the century. There's some recent studies, maybe some of you have seen that there's even greater declines expected even by the middle of the century. So there's just always new information coming out that we try to summarize in these climate trend assessments, but I can't remember if we captured all of that, but just keep in mind that there's quite a bit of variation in those estimates about how much snowpack will decline. And once again, patterns we expect across the Sierra Nevada bioregion as a whole. And I also like to make this point, and I've given this presentation in various forms over the years. Let's put these climate change projections in a little bit of context. So thinking of from the other end, going back into the recent past, the last time that global temperatures changed this significantly, as we're seeing in the 21st century, as the projections go, about 4 to 5 degrees Fahrenheit, was in the Pleistocene. And that was, about 20,000 years or so ago. Much of the southern Sierra Nevada upper montane zone, zone primarily above, let's say, 8,000 feet elevation, a lot of that was pretty much covered by hundreds of feet of ice. Death Valley was under a deep lake that was about 600 feet deep. And these temperature changes are in the opposite direction we're talking about right now. So this is how dramatic we can expect some of the changes to occur. It's really quite large and intensive at scale. And then when we think about putting climate change projections into context, going the direction we're going now in terms of increasing temperatures, the closest we can get more recently was in the mid-Holocene. And we described some of these changes in our NRV assessments. So we're talking about 5,000, 8,000 years before present. We were only about 1.5 degrees Fahrenheit warmer. And if you really want to get something that's more similar to what we're going to see based on the projected temperature increases in the region, so end of the century here in the 21st century, you have to go back 45 million years before present. Now that is a long time ago. And so it just really emphasizes that many of our ecosystems today, which have evolved to a large degree past, really came together after the last ice age period, like 20,000 to 15 or even 12,000 years ago, is in definitely in a very different climate envelope that we're seeing based on our projected increase in temperatures by the end of the century. So pretty dramatic mismatch in terms of the temperatures those ecosystems have evolved with in the past. Okay, let's shift gears a little bit to some recent projected changes in these other climate-related factors and processes we're thinking about here. So wildfires, vegetation, and wildlife. I'm just going to touch on these very briefly, by the way. So if you want more details on these, you could certainly dive more into these reports. But here's one example from a publication by Meyer et al. Published over a decade ago now, but it's still very relevant today. And there's a variety of other studies published in the Sierra Nevada and Western United States that really back these trends, which is we're seeing a significant increase in annual burned area, mean fire size, the maximum fire size, and forest fire severity over time. And this is particularly clear starting in the kind of early 1980s or even the late 1970s period, where greenhouse gas emissions really ramp up and global temperatures start to increase. So more locally in the Sierra Nevada, we can see this is having a pretty significant effect on our fire regimes in the region. And I'm going to spare you all the many figures I could show you here, but to just go over some of the trends that we're going to see in the Sierra Nevada, or we have seen recently, in that wildfires are becoming larger, more frequent, and higher severity in many of our Sierra Nevada forests. That pattern is backed by a number of published studies now, scientific studies. And the number of these studies are also looking both statewide across California and the Western US, and particularly when they're focusing on these frequent fire forests. So our yellow pine, Jeffrey pine forests, our mixed conifer forest types that evolved with frequent fire that burn primarily at low to moderate severity. We're seeing these similar patterns of fires becoming bigger, more severe, and well outside what we saw historically or naturally. In terms of future wildfires, models are projecting increases in wildfire activity and intensity in the Sierra Nevada in the 21st century. This is driven by increases in fuel aridity, decreased snow cover, increased temperatures, and other factors such as recent tree mortality, which is increasing the levels of dead and down woody fuels, which certainly increases the energy output from some of these fires. And the largest wildfires have occurred in the last decade. I've been giving this presentation for probably over 10 years in various forms. And I think if this piece has become, we don't need model studies to tell us this any longer. We can see this on our landscapes today. Just look over at the Creek Fire that burned 2 years ago, and we can see these patterns playing out on our landscapes today. So I think those models, if anything, if they were deficient in anything, they were deficient in the sense that many of these changes in our wildfire patterns are occurring even more rapidly than some of the models initially predicted. Vegetation. Let's look at some recent vegetation changes and some broad patterns in once again, the Sierra Nevada bioregion. And these are patterns I'm going to summarize primarily for the western slope, but some of these are relevant to the eastern Sierra as well. We're seeing in the 20th century into the 21st century, we've seen a loss of yellow pine dominated forests, our Jeffrey pine and our ponderosa pine forests. We're seeing an expansion of shade tolerant conifers into many of our mixed conifer and other forest types. So species like white fir and incense cedar have greatly expanded their range and their dominance. And then a loss of blue oak woodland on the west side. And many of these can be tied directly to legacy forest management, logging, fire suppression, and the like, and not so much directly to climate change. And these, let's see here. These other patterns, however, particularly as we look at increased hardwood dominated forests is one pattern. Another one is the loss of these higher elevation vegetation types of subalpine, alpine vegetation, and expansion of subalpine trees at the highest levels into previous permanent snowfields. These we can link pretty strongly to climate-related patterns. And a lot of the studies that have looked into this across the Sierra Nevada bioregion have really, in some cases, they have some circumstantial evidence, others pretty strong evidence to link these changes to climate directly. Maybe a couple case study examples here. I could just show you a couple photos. Is really exemplify some of these changes also locally or in the bioregion. Is that we're seeing a lot of conversions of forest to other ecosystem types, and this is where we could see many examples of this, especially today, where forests are converting to shrublands, and shrublands can be converting to non-native grasslands. So in the top photo, we have the pilot fire from the Stanislaus National Forest that burned in 1999. This is an area where I've done a lot of collaborative meetings in the past that I've visited myself, and this was previously dominated by ponderosa pine forest. It's converting to chaparral. Interestingly, this area reburned in the 2013 rim fire, and so the very few trees you see in that photo are now gone, and so it's primarily areas converting to shrublands now because there's just a lack of conifer seed source because the high severity patches in these fires are just so large and tremendous that there are no nearby seed trees to provide natural regeneration, where typically these stands would regenerate in smaller high severity patches. And then a more localized example on the birch fire, which burned in 2002 in Inyo. This is pinyon pine woodland that was converted to arid shrubland with some particularly some native shrub species and quite a bit of cheatgrass cover in these areas. This is an area we've done some ongoing sampling or monitoring work. And usually these systems, these pinyon pine woodland systems could experience in the historical past these stand replacing fires and they might recover. But the real game changer here is one, we have a non-native grass, cheatgrass, which is highly invasive and suppressing the growth and reproduction or regeneration of a variety of these native species. And then as climate warms, it also creates additional stressors on the system by reducing, or at least potentially reducing rates of regeneration for pinyon and other species that are important here in the Eastern Sierra. So to summarize, some of these projected vegetation changes, or actually these are the future projected changes summary. The real losers in the future that we can see in the bioregion is that, our yellow pine mixed conifer forests, our higher elevation red fir and subalpine forests, and our highest elevation alpine vegetation is expected to decline significantly in its overall extent and occurrence on our forest landscapes, especially our high elevations. And the real winners are particularly the annual grasslands. And many, unfortunately, these annual grasslands will be dominated by non-native species like cheatgrass. We can see this both on the east side and the west side of the Sierra Nevada. It's also worth noting, though, a lot of these areas, we're going to see an initial increase in shrublands, so a conversion from forest to shrublands. But these shrublands may decrease over time as they then convert to annual grasslands, as we're beginning to see more of these areas reburn in subsequent severe wildfires. And even the shrubs in some cases don't. And we're seeing this particularly in Southern California, where the shrubs just don't have, even though they've evolved with fire and stand replacing fire, they haven't evolved with a very frequent stand replacing system. And so they're converting to non-native annual grasslands, and a lot of the shifting climate to warmer climate is also favoring some of those arid adapted non-native grass species. There are a variety of unknowns though in all of these climate projections. In that, in a couple of examples, is we don't know how much or what the change is in terms of mixed woodlands and air shrublands. We know they'll probably increase, but we don't know to what extent or what species will even be favored in those vegetation types. So there's a lot of unknowns to consider as well. We expect that there's going to be some pretty significant changes in the distribution and abundance or populations of wildlife species as well. And some recent changes were summarized in some of these studies by UC Berkeley and other collaborators in the Grinnell resurvey. So what they found was that in sampling small mammal species is that many mammal species shifted upward in elevation. The alpine chipmunk is a classic example of this. It's an endemic species to the Sierra Nevada. It occurs at high elevation in the alpine environment. Its range is shrinking dramatically, and there definitely evidence of reduced populations for this species. But there are many other species where we saw no real significant changes over the last century. And then it's interesting that there's closer related species that respond pretty idiosyncratically to changes in climate and vegetation. So it's not necessarily just climate, but how vegetation changes in response to changed fire regimes and so on. And moreover, most of the upward shifts in these high elevation species seems to be pretty consistent with predicted climate warming. So I think there's a good case to be made there that climate change is really what's driving these shifts at the higher elevations. And then at these lower to mid elevations, the species ranges are most likely to be the result of other patterns or other factors such as fire exclusion. So just the removal of fire as a natural process over the last 100 or more years has really made significant changes in the distribution of these species, but not so much a factor of climate change making these changes. In terms of future projected wildlife changes for species of conservation concern like Pacific fisher and marten, it's agreed upon the published studies that they're very sensitive to climate change and that both species will experience the greatest range contraction in the southern Sierra Nevada. 60% of the coniferous bird species will exhibit substantial range reductions, including the great gray owl, another species of conservation concern in Sierra Nevada. And then about 66% of California's native flora will experience about an 80% range reduction also by the end of the 21st century. So many of these are more dire predictions that we might expect by the end of the 21st century, not necessarily more immediately. And once again, as we go further in the future, these projections become a little more uncertain. But certainly they're definitely dire predictions and cause for concern. And it's worth really noting that there's caveats always to consider when we're thinking about the projected changes. We have a pretty good, handle on what's already occurred and what's linked to climate change. But when we think about in the future, particularly as we go further into the future, these models often use some pretty simplistic assumptions and what we call these downscale climate projections using species distribution or these climate envelope models. And basically, without getting into the nuts and bolts of it, basically these projections have a high degree of uncertainty when we're thinking about individual species changes, whether it's a plant or an animal species. How much those will shift into the future is very much dependent on a variety of factors, many of which, as scientists, we don't have a good handle on some pieces of those, only the ones in terms of how much will the climate change and will the current climate envelope for that species change significantly today compared to, say, 50 or even 80 years in the future. So where we do have a greater degree of certainty, though, is these broader biome changes, such as the conversion of a forest, coniferous forest ecosystem type to non-forest. Those we have a much better handle on. And it's pretty clear that there will be significant losses, I mentioned earlier, in forests, coniferous forests across the Sierra Nevada bioregion as a whole. And as I mentioned earlier, if you want more information on this, you could go to our external website. This is in the Region 5 Ecology Program external website, which is, it's available. And you could check that out for climate trend summary for any national forest in Region 5. Not all of them have been completely updated, but for the ones for the Southern Sierra, that is the Inyo, Sequoia, and Messere National Forests, have been updated. And we're constantly trying to revise those and update those as we get new information. But typically, we don't do a full update until about 4 or 5 years down the line. And it's also worth noting, there's just a variety of other additional climate change resources out there. And this is just a very short list of online resources here. The USDA California Climate Hub maintains a lot of these. Forest Service Climate Change Resources Center, CalAdapt, the Climate Adaptation Knowledge Exchange, and of course the bedrock of scientific information coming out of the 6th IPCC International Panel on Climate Change report that really digs in a lot of the details of scientific information across the entire globe. So, I've given this, like I mentioned earlier, I've given this presentation in various forms over the years, and what I found is that when I end on my previous slide, I just leave on a very depressing note. So I thought I'd add just a few slides at the end to try to add to end on a more positive note, or one that's a little more enabling in terms of actions we want to think about to adapt to climate change in the future when we're thinking about forest and other landscapes. So what can we do about it? Well, I'm going to give you a real short, brief list of my own here. And top of the list here is ecological restoration. We can restore our ecosystems because many of these ecosystems are moderately to severely departed from what their historical natural range of variation condition was, or essentially what their condition was when they had high integrity and were resilient to a variety of stresses we're seeing playing out today on our forest landscapes. So by conducting ecological restoration, we've talked about this on previous ESCCRP calls in the past, but it's just worth reemphasizing this point again and again, is that it really helps to build resilience and adaptive capacity to stressors like climate change. And it's also worth noting that there's decades of scientific evidence of information, and we summarize a little of this in the GTR natural range of variation assessments, for example. But I know Malcolm will be adding to this growing list of really strong evidence to demonstrate how different our historical forests were compared to the ones we see today, and why restoration is so important for us to bring these back in line to a more resilient and sustainable condition in the future. And it's also worth mentioning that it's these when we do conduct ecological restoration, doing it small and piecemeal doesn't work. We really need to be effective in our restoration actions, and that's by implementing strategically and at larger landscape scales. So we're not talking about a few hundred acres, maybe here and there, and a lot of that I know is limited by capacity issues. But when we can work together and really affect change at the larger landscape scale, we're starting to talk about tens of thousands of acres. And there's a variety of examples I've listed here. It's just a short list of a few that are really obvious. Top of the list here: reduce that forest density and fuels. That's really quite apparent. Reestablishing our natural fire regimes, restoring forest structural heterogeneity, enhancing native biodiversity and wildlife habitat. Number 2, shared stewardship. This is the term that the Forest Service is using now, which I really think epitomizes what we need to do as we move forward. And ESCCRP is just a prime and excellent example of this. And so we need to form robust and strong partnerships to increase our capacity and effectiveness. So no longer is this just like a Forest Service effort. We work alone. It's something that we really do have to work collaboratively and together to affect positive change on these landscapes. I'd also put the plug in for building really strong science and management partnerships, and working with folks like Malcolm and other scientists at PSW and in the academic institutions and so on. I think are really critical for us moving forward when we try to restore our landscapes and use the best available tools that we have and approaches. And of course, the all lands approach, another term the Forest Service likes to use, I think is really beneficial here, in the sense that we're not just focused on Forest Service lands, but we're focused on the state and private lands, other federal lands, and looking at the larger and bigger picture to solving the issue, because that's the way we solve it. We don't solve it piecemeal or agency by agency or group by group. And then lastly, experimenting, learning, and adapting. I think it's something humans have done for millennia, but I think it's also easy to become trapped in institutional thinking And really that could be detrimental, or it could help, or it may not help us move forward as we're dealing with novel conditions, rapidly changing conditions, and forest landscapes that are changing pretty quickly right before our eyes. So to accomplish this, I think we need to focus on, some of those tried and true approaches we've used in the past in terms of restoration, but also consider a variety of new approaches. And I use, sorry, Malcolm, I use a lot of your examples here, but here, recent pyrosilviculture paper, I think, is an excellent example of this. This is just a publication that came out last year. In essence, it really talks about how you can combine the use of silvicultural tools with the use of fire in the landscape, combine those two together more or less in a way that they complement one another to increase pace and scale of restoration treatments. And there's a variety of other pieces of new scientific information that I think haven't been really tested on landscapes, but we can really try some of these things out, learn from them, and adapt to climate change and these other stresses over time. And then I always like to put the plug in for monitoring research, because they are absolutely key to learning and adapting to all these rapidly changing conditions. And we're not always going to have the answer. That's always going to be the case. But like I mentioned earlier, we are really good at being able to adapt to these conditions, as long as we're willing to collect some information, summarize it, and then pull that into our adaptive management process, or our collective learning process. I think that's really critical for us to move forward whenever we're thinking about climate adaptation for these types of landscapes. So that's probably my last slide. Yes, my last slide. So hopefully, Janet, I didn't go too far over my time limit, but thanks everyone for their attention. I guess if there's time for questions, I can answer it now or later.
Sure. Thanks, Mark. Really appreciate it. I think we do have a few minutes if anyone has questions. Mark, I think it might help if you take your screen share down. That way I can see the gallery a little bit better. If you guys have questions, if you raise your hand, we'll take a few. Go ahead. I see Taro. Go for it, Taro.
Hey, good day, everyone. I'm Taro Pacina with Spatial Informatics Group, also a career wildland fire and fuels manager. Great presentation, Mark. Wholeheartedly agree. And I'll just add that maybe not from an ecological restoration standpoint, but from a protection of high values at risk, including communities. Oftentimes those small treatments in close to the communities can make all the difference for fire responders to protect that particular value at risk. It's just worth mentioning, I think. That's all I was going to say.
Great point, Taro. And I think that speaks to that. I forget now my points there of affecting positive change, but to the point of being strategic about our treatments. So obviously one key piece of that is making sure we have those strategic field treatments around the community to protect it, because that's a big focus of ESCCRP and many of these collaborative restoration projects. So I completely agree with that.
Yeah, just added value. They complement each other, and it could be the cornerstone for those much larger landscape restoration needs that you aptly point out.
Yeah, agreed. Thanks, Tara.
Other questions or comments for Mark while we've got him here? I have one, Mark. Just I don't know if everyone on the call sort of gets the critical nature of the type conversion piece, but just living where I do in Swell Meadows, you had a photograph of the birch fire, which I think was 2002. So that significant change in what that vegetation looks like. And then we have, I don't know what the fire history between 2002 and 2015 was. There was probably something in there, but the round fire in 2015 that most of us who were here remember, taking out a lot of homes in Swell Meadows, that burned. And not 2 years later, we had the rock fire in Rock Creek Canyon that burned predominantly in cheatgrass. So you get more fire than is natural across the landscape with that continuous invasion of those non-native annual grasses, which can be a problem. And you don't get that, oh, well, we've had good fuel reduction for a long time, because you have those fine fuels that are persisting, and that's a real management challenge in and of itself. So just something from my backyard that I've noted.
Yeah, no, great point, Janet. Yeah, that's they're terming the classic grass fire cycle these days, where the non-native grasses like cheatgrass are just highly adapted to very frequent fire, and the native shrubs and even tree species are not. So when they facilitate that fine fuel bred, flashy and fine fuels that facilitates that rapid fire interval, that frequent fire interval, it really converts the vegetation from this, these desirable native vegetation types to one that's very undesirable of, almost complete cheatgrass cover. But yeah, that's I think one of the very concerning type conversions we're seeing right now. The other one being the big one from forest to non-forest, which in itself isn't so bad at a small scale, localized scale, little patches historically that occurred. But when it occurs and at patches that are the size of tens of thousands of acres, that's concerning. And that is not something we've seen anywhere in the historical past.
Yep. Todd, go ahead.
Yeah, so similar thing that we've seen like in the Golden Trout Wilderness, in the southern part of the forest on the west side. We've had the McNally fire like in 2002, and then especially like in the Jordan Hot Springs area. And we've had like 3 or 4 fires there in the last, 5 years. And then we had, the Sequoia complex coming through it last year, 2 years ago. And so basically we had, old growth, upper mixed conifer, west side forests. And now, especially on the south facing slopes, it's basically cheatgrass in 20 years, and I've seen it. And all the different fires, for some reason, it just keeps burning. And now we've totally changed the fuel regime and vegetation down there. So yeah, just in the 20 years I've been on the Inyo, I've seen those sort of dramatic changes.
Yeah, thanks, Todd. That's very consistent with the folks that I speak with on the Inyo National Forest, that particularly in the last 10 to 20 years, there's been some pretty dramatic changes and conversions to cheatgrass, especially in the sagebrush type, but also in the forest types, eastern Sierra forest types. And that's very concerning. That's a pattern that's not just limited here. We can see it bioregionally and across the Intermountain region as well. So yeah, that's climate change, unfortunately, is I think exacerbating that situation until maybe even some climate projections predict that even by the end of the 21st century, it gets so warm that even cheatgrass is no longer able to persist in the drier parts of the forest. But that's at a much later stage, and right now we're grappling with it.
Okay.
Just one more quick thing. Sorry, Mark, your last picture was stunning. The creek fire with high intensity as far as the eye can see. Just curious if you or Malcolm or anyone's been looking at, where those types of fires run into previous disturbances or fires, like where the creek actually hit the Lyons fire or the Dexter fire hit the Clark and the Owens River. Because while that's really terrible, all that high severity, in some ways, you're resetting the clock in some areas. And in spite of the fact that we're seeing these very large, high intensive, frequent fires, they're not all high severity, right? There is some good that's coming out of them, although we can't necessarily claim that good when people have lost their livelihoods or worse from them. But at the same time, it's another puzzle piece, right? And maybe that's a topic for another day, but your last picture was very stunning.
Yeah, that's a great point, Tara. I think what I can say, answer that more briefly, because it's a whole topic in itself, is there's no reason to think that high severity fire in itself is a bad thing. It's just that the scale and the extent of which it is burning our landscapes today has no historical precedent, and it has a number of negative effects to our vegetation, forest ecosystems, and the wildlife associated with these ecosystems. That's an emerging picture that's becoming quite clear now. So in areas of the creek fire that burned at primarily low to moderate severity, and when there's those high severity patches were primarily less than 1 to 10 acres in size, those we can consider to be largely beneficial in those parts of the landscape. That might actually be, I'm forgetting now, but the numbers might be like roughly half of that landscape might be in that condition. So I'm a little bit more of an optimist in terms of the fire effects. I like to think about, hey, there's a lot of those areas in the Creek Fire where there were those beneficial effects. But then there's the other half, right, that burned in coniferous forest ecosystem types that burned at high severity in very large patches. And when I say large, they're typically more than 250 acres in size, but the largest high severity burn patch, I know I've analyzed it, but I forget the number is in the tens of thousands of acres. That is not a good thing in the sense that it's now eliminated critical habitat for fisher and spotted owl. It's now greatly diminished many of the ecosystem services provided, whether that's wood services, wildlife habitat, biodiversity, air quality, water quantity and quality. Many of these impacts to our society are pretty dramatic in terms of those large high severity patches. And we have over a decade of post-fire conifer regeneration data from fires across the state. And one thing that's become really clear is as soon as you move about, let's say 100, 150 so yards away from the edge of those green forests, conifers are not coming back, it's shrubs. And that's because the seed source distance is too far. And as the climate warms at those lower elevations, it's also becoming less likely those conifers will naturally regenerate. So we've interrupted the natural processes of the ecosystem to recover themselves. That's why we sometimes have to take reforestation or other actions to bring them back in line with what our restoration actions to bring them back in line with what we want to see in the future. So big topic. Yeah.
No, that's great. And how about the effectiveness of previous treatments or fires that were managed? I mean, when we managed the spring fire, obviously the primary objective was protect the community of Mammoth. And initially we claimed benefits from that, but essentially we're just trying to keep up with it. But the Creek Fire did, to some degree, run into the springs. I'm sorry, the lions, not the springs, the lions. Is it safe to say that, the heartache and headache we went through and the smoke that the town had to endure paid some dividends when the Creek Fire bumped into it, I guess. And that's, again, a topic for another day if we're getting too deep here.
Yeah. And I'll keep my answer brief because I know we won't go over time, but yeah, Tara, you have many excellent questions. And this is one I'd like to spend more time. But I will say briefly that it's my professional opinion, that the 2018 Lions Fire was absolutely critical in halting the spread of the Creek Fire toward the town of Mammoth Lakes, not to mention just reducing the impacts to places down there in Red's Meadow, in the monument down there, Devil's Post Pile, and so on. I think it was just a really critical piece. And that, once again, it's not like I've analyzed it, but just from my understanding of everything that I've observed in that fire, that's what I would say. We do have some research groups at a University of Washington and other collaborators, UC Davis, UC Berkeley, that are beginning to look into this question from a scientific standpoint. So hopefully, stay tuned. We'll have more information on that. But I can't say, based on information we published, including stuff I've been involved in myself in the past, that those, quote unquote, managed wildfires that we managed for research objectives have burned under ideal, low to moderate severity conditions that have benefited these ecosystems. And there's a variety of circumstantial or even better evidence to show that they do halt the spread of undesirable wildfires in the landscape. So they really benefit us in a number of ways, and they do it at a fairly large scale. So there's a lot of benefits of those fires, and I think the Lions Fire is one example of that.
Thank you so much, Mark.
Thanks, you guys.
Yep.